9.9 Cell potential under non-standard conditions. Our outcome is I can explain the relationship between deviations from standard cell conditions and changes in the cell potential. So we want to be able to explain how if we have a non-standard cell, how does that change the voltage that we can achieve? So when Germany invaded Denmark in World War II, Hungarian chemist George de Hevesy dissolved the gold Nobel Prizes of German physicists Max von Laue and James Franck. He dissolved them in acid to try to prevent the Nazis from confiscating them. So the idea is that if he could dissolve those gold medals, they would sit in solution on a shelf somewhere, and when the Nazis came to check for valuables, they wouldn't find anything. So we're going to use these standard reduction potentials to predict whether or not 1 molar nitric acid is going to dissolve gold metal to form a 1 molar gold solution. So if we just look at the standard half reactions here, so one of these half reactions is going to run as a reduction and one will run as an oxidation. So in these two reactions here, if we look at the voltage, whenever we combine our half reactions, we get a negative voltage. And we discussed how when you have a negative voltage, that reaction would be non-spontaneous. So based on this, we predict that the gold metal is not going to dissolve in 1 molar nitric acid. What if we used 0.1 molar nitric acid? Now, a little bit of thinking about this lets you predict pretty easily that the answer is probably no. If 1 molar nitric acid isn't going to do it, then 1/10 of the strength probably isn't going to do it either. So let's go ahead and calculate what E cell is going to be here under the non-standard condition of 0.1 molar nitric acid. I'm going to predict that my value for E cell, my voltage, is going to be more negative than my current voltage. So we're going to go ahead and use the Nernst equation here, and I'm using the one that has all of the constants combined into one number here. So there's a couple of things that we need to know in order to solve this equation here. So E cell is going to be my non-standard conditions. E cell is going to be my standard conditions. Now we just solved for that in the previous problem. N here is going to be my number of moles of electrons. And we're going from gold 0 to gold +3. And we already looked at our half reactions, and they both had 3 electrons. So N is going to be equal to 3 here. The next thing that we need to know is Q. So Q is the reaction quotient here, and it is calculated in the exact same way that K is calculated. So in order to solve for Q, remember that we don't want to include any solids or liquids in our expression. So we end up with this Q. Now we want to make 1 molar gold solution. So that's going to be a concentration of 1 molar. And it says that we're going to have 0.1 molar HNO3. So we could predict here, these guys are both going to be 0.1 and 0.1. We get that from the nitric acid dissociating. And NO here, this is going to be what we produce. So based on the fact that nitric acid is limiting here, this is going to be 0.1 also. Now, when you calculate this, we end up with a number that is more negative than our original E cell here. So that makes sense. If 1 molar nitric acid couldn't do it, couldn't dissolve it, then 0.1 molar certainly isn't going to do it. Now, why does this happen here? So we've got our standard state voltage here. And then remember that this guy is just a big old correction factor here. So this correction factor takes into account us not having standard concentrations with our Q calculation here. Now, if you calculate the value of this ratio, you end up with something that's going to be less than 1. So this is going to be non-spontaneous, as E cell is a more negative number. Now, if you look at this Q value here, it's a little top-heavy. So that indicates that this needs to shift towards reactance. So the reverse reaction is more favored. Another way of saying that is that it's less spontaneous. So for each of these, we want to predict whether the E cell is larger or smaller than E naught cell for the following cases. So we have our standard voltage here. And we want to try to predict if I use these different concentrations, would I get a bigger voltage or a smaller voltage? So remember that in this equation, we have Q here. So I can write Q for this equation. Remember that we aren't going to include any solids. So I'm going to put my aluminum plus 3, and that needs to be squared, over my Mn plus 2, which needs to be cubed. So if I plug in a value of 2 molar, and I plug in my value of 1 molar, my ratio here is a bit top heavy. So that means that my reaction is going to shift towards the reactants. So that's in the opposite direction. So the concentration of a product has been increased over 1 molar. So that's going to favor the reverse reaction, which means that the non-standard voltage that we measure here is going to be less than the standard voltage of 0.48. Now we can apply this same reasoning to our other problem here. So I'm going to plug in my aluminum plus 3 on top, that's 1 molar, and my Mn plus 2 is 2 molar. So now this ratio becomes a little bit bottom heavy here. So that means there's too much products. So this is going to favor the forward reaction. You could also think of this as a Le Chatelier problem as well. So since we're increasing the amount of a reactant here, that's going to favor our forward reaction. So E cell, whatever it is going to be bigger than my non-standard voltage. So here we have a galvanic cell that is constructed of the following half reactions and conditions. So these are all non-standard here. So let's first calculate the standard voltage here for this cell. Now, the more positive voltage is going to run as is as a reduction, which means that this guy is going to be my oxidation. So I have to flip my oxidation reaction so that I have electrons being produced as well as consumed. Now, looking at my two half reactions here, I can see that there's 2 electrons being transferred in my bottom equation. So we need to balance that. So we're going to double the top equation. That way I'll end up with 2 electrons being produced and then 2 electrons being consumed. So I'm going to go ahead and combine and cancel these equations together. And we end up with a standard cell voltage of 1.76 volts. Now the reason we get such a big voltage here is due to the pulling ability of zinc on electrons versus this other half cell here. Zinc really wants to lose electrons. It's high on the activity series. It gives up electrons. So it's paired with a cell that has like a deep thirst for electrons, really wants to try to absorb electrons. So since there is that difference in their potential, we end up with a large E cell, a large voltage here. So now let's calculate E cell under these non-standard conditions. So we're going to have a little bit of work to do here. We already know E naught cell. We just calculated that in the previous slide. We also know that the number of electrons, number of moles of electrons, is going to be 2 here because we previously balanced. So then we'll need to calculate Q, and then we'll need to plug in all of these values and solve to see what our E cell will be. So to calculate Q here, we have Zn plus 2 and VO2 plus squared, so that's our products. And then on bottom, we have our reactants. Now, if we look at our concentrations, we are taking a couple of these below the 1 molar, and we're taking a couple of these above 1 molar. So nothing's at 1 molar here. So we plug in all of these values here. Notice that Q here is going to be a little bit bottom heavy. So we're going to end up with something that has too much reactants. So the forward reaction will be favored, meaning that my non-standard voltage is higher than my standard voltage. So we want to go ahead and complete this diagram here, drawing in the cathode and anode, the components, and the flow of electrons. So zinc here is going to be my anode. Now remember an ox and red cat. So reduction occurs at the cathode and oxidation occurs at the anode. So that's how I know I want to put zinc here, because zinc is being oxidized. Now, in my reduction, we don't have any solid. We don't have any electrode there, any metal that can act as an electrode. So we're going to need to use a platinum electrode. So this is just an inert electrode that facilitates the reaction. It's not going to react with anything, that's why it's called inert. And then we can go ahead and label both of these solutions with the ions and concentrations that they contain. So electrons flow from anode to cathode. Zinc really wants to give up electrons high on the activity series, and the other half cell really wants to consume those electrons. So our voltage here is above our standard voltage because our forward reaction is favored under these non-standard conditions. So your reflection questions: explain how finding cell potential under standard and non-standard conditions is different. What happens to the cell potential when an electrochemical system reaches equilibrium? And how does this relate to a dead battery?